All right, ladies and gentlemen, here we got the notes for section 10.1, which is the power series. So we're going to start with a geometric series, an infinite series to begin with. An infinite series is an expression of the form a1 plus a2 plus a3, so on and so forth, up for an infinite number of terms. So a of k is just how you find the terms. The numbers a1, a2, and blah, blah, blah are the terms of the series. An is the nth term. So you can also form a sequence with the partial sums. So S1 is just the sum of the first term. S2, sum of the first two terms. S3, first three terms. So on and so forth. So Sn is the sum starting at the first term up to the nth term of your equation. And then it continues on forever because this is an infinite series. Of real numbers, each defined as a finite sum. If the sequence of partial sums has a limit, as n approaches infinity, we say the series converges to the sum S, and we write this. Otherwise, the series diverges. Okay, so example 1. Does the series 1 minus 1 plus 1 minus 1 plus 1 minus 1, so on and so forth, converge? So what we need to look at is the list of sums and see if they level out. So S1 is just the sum of the first term, 1. S2 is the sum of the first two terms, 0. S3 is the sum of the first three terms, 1. S4 is the sum of the first four terms, 0. So since these numbers do not level off at a given value or approach a value for S, this diverges. Now you have to be careful because if you look at the pattern, it's tempting to pair them off, 1 minus 1, 1 minus 1, 1 minus 1, so on and so forth, getting 0 plus 0 plus 0 plus 0. But this is infinite, it goes on forever, so you can never stop closing your parentheses, so you can never actually evaluate it. So we can't work that out. Okay, does this series converge? So S1 is 3/10. Now I'm going to change the decimal, so that's 0.3. S2 is the first two terms, which is 0.33. S3 is the first three terms, 0.333. You can see where this is going. Sn will be 0.3 repeating, which means this does have a limit of 1/3. So it converges. Okay, so the infinite series, blah, 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 converges, then the limit of each term approaches 0. So if you notice, this means the limit of a of k as k goes to infinity is not 0. The series must diverge. So this is each term, not the sums. So like here, if you look at this, that's 0.3, this one's 0.03, 0.003, so on and so forth. So these individual terms are approaching 0 as n gets larger. The geometric series, a plus a to the r plus a to the r squared, given by this formula, converges to the sum a over 1 minus r if the absolute value of r is less than 1, diverges if the absolute value of r is greater than or equal to 1. The interval from -1 to +1 is referred to as the interval of convergence. Okay, so example 3 here. Tell whether each series converges or diverges. If it converges, give its sum. So let me jot that down. We'll write the formula down here real quick. A over 1 minus r if it does converge. So the first thing we need to look at is our value for r. So for this problem, r is equal to 1/2. The absolute value of 1/2 is less than 1, so this will converge. In order to get it to converge, I need to look at my values. So for this one, our a is here, 3, r is 1/2, so this will converge to 3 over 1 minus 1/2, which is 3 over 1/2, which is 6. So this series will converge to 6. Which way do we want to go? We'll go down. So here, our r value is -1/2. So the absolute value of -1/2 is less than 1, so this will converge. For this problem, our a value is 1, because it's 1 in front here. So 1 over 1 minus -1/2, which is 1 over 3/2, or 2/3. So this series will converge to 2/3. If you add up all of these fractions, they'll level off at 0.6 repeating. Alrighty, so up here, our r value is, 3/5. So r is 3/5, so the absolute value of 3/5 is less than 1, so it will converge. Our a value is 1. We've plugged 0 in for k, gives you the first term. So 1 over 1 minus 3/5. So 1 over 2/5, which is 5/2. So here, this one's a little bit trickier because it doesn't give us the formula, but to find the value for r, you take any term and divide it by the term in front of it. So this is going to be pi squared over 4 times 2 over pi, which ends up reducing to pi over 2. So the absolute value of pi over 2 less than 1, this is false. Pi over 2 is 1.75. So this series diverges because this number is not less than 1. Okay. So representing functions by series, a power series, and the expression of the form Cn x to the nth, so C0, C1 to the x, C2 to the x squared, so on and so forth, is a power series centered at x equals 0, because the x's all just have powers on them, or an expression of the form this is centered at x equals a. The term Cn x minus a to the nth is the nth term, the number a is the center. So these c's are just constants, they're the coefficients, so on and so forth. Okay, so let's look at what we got next. All right. Given that 1 over 1 minus x is represented by the power series 1 plus x squared, so on and so forth, on the interval -1 to 1, find a power series to represent 1 over 1 minus x squared. So let's see here. So the thing we know I can notice is 1 over 1 minus x squared is the derivative of 1 over 1 minus x. Oh, sorry. Put this is like that. Which means that if this is the power series for 1 over 1 minus x, if I take its derivative, because this is equivalent to this, I will get the power series. So what we can do is we can do this. So d over dx of 1 minus 1 over x is equal to d over dx of 1 plus x squared plus blah, 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 x to the nth plus blah, 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 forever. Okay, so over here, this becomes our thing we're looking for. Over here, this becomes 1 plus 2x, so on and so forth. So the next term would be x cubed, so it's going to be, the derivative would be 3x squared, then 4x cubed, so on and so forth. So if you look at what's happening, this nth term is going to be, the n's going to come out front, and then x to the n minus 1. So here is your power series that represents 1 over 1 minus x squared. Okay. So term by term differentiation. So if f of x is the sum, power series converges for x minus a less than capital R, then the series, the derivative, also converges for x minus a less than r and represents f prime of x on the interval. The series f converges for all x, and so does the series for f prime. So given that 1 over 1 plus x has this power series, find a power series to represent the natural log of x. So the thing you can notice is that, how do we want, notation-wise, how do we want to do this? The antiderivative of 1 over 1 plus x is equal to ln x. So what that means I can do is I can take the antiderivative. So if I want to find this, I know that this is true. So, forgot my dx's. So this over here is the natural log of 1 plus x. Over here, this is going to be x minus 1/3 x cubed. Oops, I got too many variables. That should just be x. Oh, no, I've messed it up. So x minus half x squared plus 1/3 x cubed minus 1/4 x to the 4th plus dot, dot, dot. So this term is going to be negative 1 over n x to the n minus 1. Nope, that's not right. I'm going to do plus 1, plus 1. Here, we'll write it better so you can see clear. So when you do the antiderivative, you add 1 to the exponent, and you divide or multiply by its reciprocal. Now, since it's negative, there's going to be a negative out front here. So there we go. Actually, we'll do this. The reason that happens is that this is the same thing as negative 1 to the nth, x to the nth. So we just leave that out front because it's a coefficient. So there you go. Okay. So that was term-by-term integration. So gives you this lovely formula, which is pretty much just the integration formula. You count up the exponent, divide by the reciprocal, or multiply by the reciprocal, divide by the new exponent. So this just says that if f converges in some interval, then so does the antiderivative. All right, and that is the end of the section.